Welcome to another session. In today's lecture, we will talk about SDN data plane and OpenFlow protocol. In the last lecture, we studied the architecture of software-defined networking, and we were focusing on two components or two layers of the architecture, the data plane and the control plane. So in today's lecture, we are going to further elaborate or focus on the data plane. The objectives for this lecture is that at the end of this lecture, you would be able to present an overview of the basic functions of the SDN data plane. In addition, you would be able to understand the concept of OpenFlow, which is like a logical network device. And then to go further deeper, you will also be able to describe and explain the OpenFlow tables, like the flow tables, group tables, and pipeline concepts like that. In summary, you would be able to explain the basic operation of the OpenFlow tables and pipelines and things like that. So the contents for this lecture are as follow. First, we will have a recap, a quick overview of the SDN architecture that we have seen in the previous lecture. Then we will focus on SDN data plane, what it is and what are the components inside the data plane, and also different type of tables that are actually used in OpenFlow. First, we will see what OpenFlow is, which is like a logical network device, its environment, and the components inside this OpenFlow switch, which are normally in the form of tables. So let us start with the SDN architecture. As you can see in the figure, we have different layers. At the bottom, we have the data plane layer, where we have the actual devices. It could be physical devices or it could be virtual. Normally, we called them the switches. It is important to remember that a switch could actually refer to any network device. In this context, switch doesn't mean the layer, the switches that we actually used in the networking. It could be a switch, it could be a router, it could be a bridge or any other network device. So this is the data plane where we have the actual physical or even virtual devices, and it is connected with the second layer at the top, which is known as the control plane. The main component of control plane is the SDN controller, and all the functionalities are defined here. Okay, so the actual data forwarding happens at the data plane, and the control functionalities are implemented on the control plane layer. At the top, we have the application plane where all the application exist, and you can see different APIs in between them, like the northbound, southbound, east and west. And we talked in details about these APIs and these layer in the previous lecture. So now let us bring our focus to the first layer, that is the data plane layer. So in this lecture, we are going to focus on the data plane layer, the devices, and the different types of tables. What is actually the SDN data plane? The SDN data plane is also known as the resource layer because all the resources, even physical or virtual, they exist at this layer. And it could also be referred as the infrastructure layer. Okay, because we are talking about the actual devices. So this is actually our infrastructure. So different names are there to refer, which actually refer to the SDN data plane layer. It could refer as a resource layer or even as an infrastructure layer. And this is the layer or the plane which actually is responsible for forwarding the packets. So we can say that the switches are actually the network forwarding devices that actually perform the transport of the packets, and even processing of the data packets, but according to the decisions, and those decisions are made by the SDN controller, which exist in the SDN control plane. So the important characteristic of the network devices in an SDN network is that these devices perform a simple forwarding function, and these devices do not have embedded software to make autonomous decisions. And that is the beauty of SDN. The software is at the top. It's like a generalization. Okay, because that was a limitation of the traditional architecture, that every device has a built-in software inside it. Okay, so now we separate the two things. Hardware is separate from the software. Now let us see the data plane functions. For that, to understand the functions that are performed by the data plane network devices, we need to consider this figure. Actually, this figure illustrates the different functions that are performed by the network devices operating at the data plane layer. Okay, and these networking devices are commonly referred by switches, or even you can refer to them by network elements. So they are either network elements or network switches or SDN network devices. Well, you can see that we have some elements like the forwarding tables, the different types of input and output queues, and we also have some ports. We also have some APIs and things like that. First, let me talk about the functions of this network device. Actually, it performs two functions. The first function is the control, and the second function is related with data forwarding. Control support function. Actually, you know who is controlling? The control is in the hands of the SDN controller. So this network device needs to interact with the SDN control layer. And for that we have APIs available, programmable APIs. This switch will actually communicate with the controller, and the controller will manage this switch with the help of an API. And that API is actually the OpenFlow, and we have already seen in the architecture, if we want the communication between SDN controller and these networking devices, these switches enable, then that is possible with the help of OpenFlow. So that is the first function, control support function, and for that this device must interact with the SDN control layer or with the SDN controller, and you can see it from here as well. Okay, the next function performed by this network device is the data forwarding, and that is the actual responsibility of this layer or this device to forward the packets. It will accept the incoming data flows from other network devices and even from end systems, and then it will forward them along the data forwarding paths that have been computed and established according to the rules. But again, those rules have to be defined by the SDN control layer. Okay, so the rules are copied from there We actually followed them here for forwarding the packets. So these are the two functions. The first functionality is related with the communication between the two modules, and the second one is related with the forwarding of the packets according to the rules already been established. These forwarding rules used by the network devices are actually embodied in the forwarding tables. You can see we have forwarding tables just like we have forwarding tables in the routers. So we have forwarding tables here in these devices. And these forwarding tables are used to define, to embody the different forwarding rules. And it actually indicates what is going to be the next hop in the route to forward the packet. So arriving packets may be placed in an input queue. Why we need this input queue? Because it is possible that the network device is busy in processing some other task. So the incoming packet need to wait here in the input queue for some time. And the forwarding packets are generally placed in the output queue. Now, why we need the output queue? Why don't we just forward the packet straight forward? Because it is possible that the packet needs to wait before transmission. Some processing delay could be there. Maybe other packets arrived earlier and they're also waiting for transmission. So that is why we need input queue as well as output queue to accommodate the incoming packets as well as the outgoing packets. And this figure actually shows the ports with these arrows. However, the names of the ports is not mentioned. We will see it in the coming slides. What are the different types of input output ports available? Normally here we have three types of I/O ports. One providing control communication with the SDN controller, and the other two ports are for the input and output of data packet. And this is actually a simple example. The network device may have multiple ports to communicate with multiple SDN controllers, and they may have more than two I/O ports for packet flows into and out of this device. Now let us see or let us talk about the second component, which is known as OpenFlow. As we just saw in the figure, data packets flows, and this flow actually consists of a stream of packets. It could be IP packets. It may be necessary for the forwarding tables to define entries based on some fields in upper level protocol headers. You know that when a data packet travel from one layer protocol to the other layer protocol, we actually add some control information to the data. Okay, so here the packets are actually arriving from other protocols like TCP, like UDP, like IP, or some other transport or application layer protocols. So the network device have to examine the IP header and possibly other header as well in each packet, and then it will make a forwarding decision. Now, the OpenFlow logical network device is actually a concept which is fundamental to the SDN, and mostly it is related with the practical implementation of the SDN. SDN is a concept. If you want to implement it, you would need to fulfill two requirements. What is the first requirement? The first requirement is that there must be a common logical architecture. Remember, we are talking about openness, so there must be a common logical architecture. Okay, that must be applicable on all devices, common architecture. So there must be a common logical architecture, and this architecture must be implemented on all switches, all routers, and other networking devices, and they could be managed by the SDN controller. Now, this logical architecture may be implemented in different ways on different vendor equipments and even in different types of network devices. But as long as the SDN controller sees a uniform logical switch functionalities, then the things is okay. That is the first requirement, that we need a common logical architecture. The second requirement is that we need a standard as well as secure protocol, because we are talking about communication and that is not possible without the help of a protocol. So we need a protocol between the SDN controller and the network device, and that protocol is actually the OpenFlow protocol. So sometime we would refer to OpenFlow as an architecture, sometime we would refer to it as a solution, sometime a protocol, sometime API, and sometime other names. These requirements are actually addressed by the OpenFlow, which is both the protocol between the SDN controller and the network devices, and also a specification of the logical structure of the network switch functionality. And this OpenFlow is defined by the OpenFlow Switch specification published by ONF. And you know what is ONF? We have talked about ONF in the previous lecture. So this is the introduction of OpenFlow. We have to dedicate several lectures to study this OpenFlow. But here in this lecture, we are just scratching the surface of the OpenFlow. Let us see how OpenFlow environment is. This figure actually indicates the main element of an OpenFlow environment. And you can see it consists of the controller. We have the SDN controllers. And this SDN controller, they are actually running the OpenFlow software. Other software as well, but OpenFlow software is the main component. And then we have the switches, and these switches are OpenFlow switches, because OpenFlow is implemented over here. And the third component is the end system, because this whole setup is for these end systems. Okay, so this is the OpenFlow switch context or the environment, and you can see two different types of communication. One, the bold lines or the double that you can see here, the double headed arrows lines, they are actually representing the communication between the switches and the controllers, and it is based on the OpenFlow protocol, and that is implemented over TLS, but for the time being ignore this term TLS. And we also have the data communication, data flows, and you see the data actually flows between the end system and the OpenFlow switches. And also there is a horizontal communication of data flows between different switches. Now let us see what is inside an OpenFlow switch. Here we go. Now we have zoom the OpenFlow switch. This figure displays the main components of an OpenFlow switch, and you can see an SDN controller on the top. It could be one controller, it could be more than one controller, depending on the scenario. So in this case, we have two controllers. And as we saw from the previous, we know from the previous slide that these controllers communicate with these switches, and these switches are actually OpenFlow compatible switches. Not every network device would be able to communicate with the controller. Only the devices that are OpenFlow compatible would be able to communicate with these OpenFlow controller. Okay, and for date communication, we would be using OpenFlow protocol, and this protocol run over TLS. TLS stands for Transport Layer Security. Now, each OpenFlow switch connects with other OpenFlow switches. This is actually, we have shown a single switch, but we know that there is a connection between two and more than two OpenFlow switches. And possibly they are connected with the end user as well. As we can see, end system and devices. There is a connection between the switch and end devices as well. And as I just mentioned, the devices are actually the sources and destination of the packet flow. On the switch side, this interface, or there is an interface which is commonly known as OpenFlow channel, and these connections are possible through OpenFlow ports. So we have the OpenFlow ports and we have these channels, and these channels could be connected to the end device, or maybe it could be connected with other switches, OpenFlow switches. And these connections are with the help of OpenFlow port. Now, what is an OpenFlow port? You know the concept of port, input, output ports. So the OpenFlow ports, they actually connects with the system. They also connect with other OpenFlow switches, and even they have to connect with the SDN controller. So based on these requirements, we actually have three different types of ports. I will not go into the deeper details of these ports, but just to mention their name. The one type of port is known as physical port, which correspond to a hardware interface, as the name indicate, hardware interface of the switch. And it could be an Ethernet switch, for example, or it could be anything. And then we have another type of port which is known as logical port. And as the name indicate, it does not correspond directly to a hardware interface for the switch. Logical ports, they are like abstractions being defined in the switch. And finally, we have some reserved ports that are defined by the or in the OpenFlow specification, which specify the generic forwarding actions such as sending to and receiving from the controller, flooding, forwarding, etc. But forget about the details of these ports. Just you need to remember that there are different types of ports, like the physical port, the logical port, and the reserved ports. Also, the OpenFlow specification define different types of tables, and they are very important. So the tables, normally we will be focusing on three types of tables which actually exist in this logical switch architecture. We have a flow table. As you can see, actually we have multiple flow tables. And flow table, as the name indicate, they actually match the incoming packets to a particular flow. Here the packets are transmitting in the form of a flow. So this table will match the incoming packets to a particular flow and specify what functions are to be performed on those packets. And we will see in a moment that there may be multiple flow tables. We are not talking about just a single flow table. There are going to be multiple flow tables. Okay, and we also have, beside from flow table, we have some group tables. And a flow table may direct a flow to a group table, which may trigger a variety of actions that affect one or more flow. So you can assign different flows to a group. Okay, that is the main concept. And beside from flow table and group table, we have another type of table that is not mentioned here, but that is important, which is known as meter table. And meter table can trigger a variety of performance related actions on the flow, like quality of experience, quality of services, etc. So if something is related with performance, then meter table could be used. It is helpful to define what is mean by flow. We are talking about flow. So what is actually a flow? In the context of SDN, a flow is a sequence of packets that are traversing a network, but those packets must have to share a set of header fields value. You know, a packet has many fields and some of fields has data from the upper layer. So for example, a flow could consist of all the packets that have the same source and destination address. If multiple packets are generated from the same source and they are addressed for the same destination, then you can consider them as a flow. Okay, even in the case of a virtual LAN, you can make a flow of different packets that have the same virtual local area network identifier. Okay, so if I have a message, for example, for all the students, if I want to address all the students, then that could be like a flow. Okay, because the source address is same, the destination address is same. So flow is actually a sequence of packets that are traversing a network, but they share some common properties. That is a flow, the definition of a flow in the context of the SDN. Well, now we talk about flow. Let us see, we talk about the flow table also, the group table, the meter table. Let us see, let us zoom what is actually inside this flow table. So we are opening individual components and we are going into the details of the subcomponents. Now here is the structure of a flow table. You see there are different fields. This is actually a building block of the flow table. Each packet that enters a switch passes through one or more flow tables. Each flow table consists of a number of rows, like entries. Every row is an entry. And we have 7 different columns. You can call them 7 different components. Within each flow table, we have 7 different components. Okay, and we have different entries. Every row is considered to be an entry, and we also have sub fields. Like you can see, a field of a flow table could have multiple entries, multiple required fields. We will not go into the details of all these fields, but the most important one, I would just give you a clue. First, the match field. It is used to select packets that match the values in the fields, subfields. Okay. Then we have the priority, a relative priority of the table entries. A packet enter into a flow table, what is going to be the priority? Okay, 0 for example will means low priority, and 10 would obviously mean high priority. Then we have the counter field, and this is used for matching packets as well. And inside the specification, different counters are defined, but we will not go into the details. For example, what is going to be the duration, there is a counter. What is going to be the reference count variable value, what is going to be the received number of packets, etc. Count, different types of counters. Instruction is important, by the way, and instructions that need to be performed if a match occurs. So if an incoming packet in the flow table found a match with an entry, then what instructions need to be performed, or you can say what actions need to be performed. Timeout. If you studied the TCP/IP protocol, you must be familiar with the timeout concept. That is the maximum amount of time a packet would stay inside this flow table, like the lifetime of the packet inside the table. And there are two types of timeouts. One is known as idle timeout and the second one is known as hard timeout. There is a little difference between the idle and hard timeout. Actually, okay, we will not go into the detail, but there is, if somebody is interested, you can raise the question during the class. What is the difference between the idle and hard timeout? Then we have cookie field, and it is chosen. This value is actually set by the controller. May be used by the controller to filter flow statistics or maybe modification, flow deletion, etc. Things like that. And flags, as you know the concept of flags, actually they alter the way flow entries are managed. So you can set different types of flag based on conditions or requirements. Okay, so this is about the flow table structure, and if we open the match field, it has certain things inside it. For example, ingress port, egress port, Ethernet, SA for source address, DA for destination address, the type of Ethernet, IP port, whether it is IP version 4 source destination or IP version 6, TCP source, TCP destination, UDP source, UDP destinations. You see, this is the information that come from the upper layers. Okay, header files, ingress port, the identifier of the port on this switch on which the packet arrives, egress, the identifier of the egress port, like we will see the difference between ingress and egress in the next slide. And then we have the addresses, different type of addresses. These addresses could be exact addresses, or they can use the concept of wildcard, like arrive from any source or destinated to any end system, like multicasting or broadcasting, etc. Then IP, whether it is version 4 or version 6, and things like that, TCP, UDP information. Well, these are mandatory fields. We also have subfields that are not mandatory, but they are like optional. For example, the physical port, metadata, VLAN address identifier, and ICMP, ARP, different type of protocols, ICMP version 6, tunneling information, TCP flags, IP version 6, extension fields, and plenty of things are there. If you are interested in the full structure of this flow table, you can refer to the specification. Okay, now OpenFlow can be used with network traffic, which involves a variety of protocols and network services, for example, IP, TCP, UDP, etc., and other protocols as well. Okay, so this was about the flow table. We also have the structure of a group table mentioned over here. I think our last slide is going to be about the group table. For the time being, let us skip the group table. We will come back to it, to the concept of group table at the end of this presentation, hopefully. Okay, so next let us see what is inside this instruction field. Actually, this instruction field is also a basic component of the table, and the entries consist of a set of instructions that are executed if the packet matches the entry. Okay, as I just mentioned that these instructions would be executed if there is a match between the incoming packet data fields as well as the fields of the flow table. If there is a match, then these instructions are going to be executed. And what are those actions? Actions actually describe packet forwarding or packet modification or assignment of the packet to a group table where different operations could be performed, things like that. Again, the OpenFlow specification include different types of actions that are to be performed. For example, forwarding a packet to a specific output port, there is one action. Beside, we can set a queue ID for a packet. Remember, input queue, output queue. So which queue the packet has to occupy if it needs to wait for input or output processing. When the packet is forwarded, for example, to a port using the output action, then the queue ID determines which queue attached to this port is used for scheduling and forwarding of the packets. And also if we need to send the packet to a group of tables, so the group number should be there, and other fields like TTL, like drop the packet, push the packet, pop, etc. But different fields are there. You can, if you are interested, you can go to the specification for further details. Now let us see what is actually pipeline. You see the we are actually opening the component of this OpenFlow switch. We saw details of the flow table, we discussed the ports, we discussed the controller, and now let us see what is the concept of a pipeline. Actually, the flow table pipeline, as you can see, a switch include one or more flow tables. Here you can see we can have more than one flow tables. Okay, so a switch includes one or more flow tables. If in scenarios where more than one flow tables are required, then we need to organize them as a pipeline. And for that, the tables need to be labeled with numbers starting from 0. And this pipelining concept actually provides the SDN controller flexibility. That is the beauty of using the pipelining approach in the SDN. You know the concept of pipeline. Several tasks are executed parallel. Okay. The OpenFlow specification defines 2 stages of processing. As I just mentioned about something about the ingress and egress. So the OpenFlow specification defines 2 stages of processing. One is ingress, the other one is egress. In the ingress processing, it always happens with the first table, for example, table number 0. If table number 0 is the only table, then the ingress processing is very simple because it has to process only that single table and there is going to be no role of the egress processing. But in case we have more than one tables, then egress processing will involve. It is actually the processing that happens after the determination of the output port. You have specified what output port the packet or the flow will take. Then it happens in the context of the output port, as the name indicate, E for exit, egress processing. This stage is optional because it depends on the ingress processing and the number of tables. But if it occurs, it may involve one or more tables at this level. So in short, the pipeline processing always starts with the ingress processing at the first flow table, and then if there are more than one tables, then we can actually forward it to the egress processing. And this pipeline process will actually provide flexibility to the SDN controller. Okay, next let us see again how the use of multiple table can enhance the functionality and how actually they work. So the use of multiple tables and multiple flows, it actually enables the nesting of flows, or put another way, it actually enables the breaking down of a single flow into a number of sub flows but parallel. You can see parallel sub flows are actually provided as an input to another flow actually tables. So the use of these multiple tables, more than one tables, they actually allow us for nesting the flows, or allow the transmission of nested flows, or if you put it in another way, so the breaking down of a single flow into a number of subflow that actually execute parallel pipeline concept. Okay, and in this figure you can see an example, an entry in table 0. We have three tables, table 0, table 1, table 2, which is going to be the first table, table 0. Okay, so let us focus on this example. We have an entry to this table 0, and this entry actually define a flow which consisting of packets, and these packets are traversing the network from a specific source IP address to a specific destination IP address. Means they have same source address, same destination address. Once we have calculated the least cost route between the source and destination endpoints, it might make sense for all traffic between these two endpoints to follow that route, because they have same source and same destination. So why not to send them to the same route? And the next hop on that route from this switch can be entered in table 0. So all these flows are actually for the same destination and they're generated from the same source. So why not to put them together? Okay, so that they can follow the same route toward the destination. And for that we are actually providing them as an input to table number 0. In table number 1, you can see, if you focus here on the table number 1 entries, we have separate entries for this flow. So separate entries for this flow, we have defined them. Why? Because for different transport layer protocols, you know, at the transport layer we can have TCP and we can have UDP. So we have a flow dedicated to the TCP packets and we have a flow that is dedicated to the UDP traffic. So for these sub flows, the same output port might be retained so that the sub flows all follow the same route toward the destination. However, TCP includes congestion control mechanism, and that is not normally found in the UDP. If you are familiar with the TCP UDP concept, their differences. So TCP is congestion oriented. Congestion control mechanism is there, while UDP does not follow congestion control mechanism. So it might be reasonable to handle the TCP and UDP subflow differently. Why? In terms of quality of service. So if you divide the TCP subflow into a separate subflow, then it could be easy to provide different types of quality of service for different flows. Now any of the table 1 entry could immediately route its respective subflow to the output port, but some or all of the entries may invoke table 2. You know, you can see here table 2 further divides each subflow. The figure shows that TCP subflow could be divided. As you can see, we can divide them into further subflows, like FTP is using TCP, SMTP is using TCP. So we have a different subflow for FTP, we have a different subflow for SMTP, and maybe we have a different subflow for another type of traffic. Okay, so SMTP, Simple Mail Transfer Protocol, or File Transfer Protocol, as these applications are running on top of TCP, so you can divide TCP subflows on the basis of the protocol that is actually running on top of TCP or UDP. Similarly, UDP flows could be subdivided based on the protocols that it actually runs on top of the UDP, such as SNMP, which stands for Simple Network Management Protocol, and the figure also indicate other subflows at table 1 and 2, which may be used for other purposes. Okay, so these are actually the flows which are coming from table 2 to table 1, and table 1 has different subflows, and these are provided as an input to table number 0 because they have same source and destinations. For this example, it could be possible to define each of these fine-grained subflows in table 0. The use of multiple tables in this case, for example, simplifies the processing in both of SDN controller and OpenFlow switch. So all this division, the concept of pipelining, the concept of using flows, multiple flows, subflows, it actually fine-grain the whole concept, and it actually simplify the processing in terms of quality of service, in terms of management, in terms of processing, in terms of forwarding, and things like that. Now, as I just mentioned, that we will come back to another component, that is the group table. So finally, let us see what is inside this group table, and I'm sure this is going to be the last slide, so stay there. Okay, now in the course of pipeline processing, a flow table may direct a flow of packets to the group table. Remember, sometime we need to forward the packet from the flow table towards the group table rather than another flow table. As you can see here, we are forwarding the table from one flow table to another flow table and then another flow table, but sometime the case could be like this. We need to forward the flow table, we need to direct the flow of packets to the group table rather than another flow table. The group tables, and mostly we have group actions that enable the OpenFlow to represent a set of ports as a single entity for forwarding the tables, for forwarding the packets. That is the main concept, like a group. Now we are talking about the groups. Okay, so the group table and the actions that are performed on the groups, it will actually enable the OpenFlow to represent a set of ports, not a single port, a set of ports, but this set of port could be represented as a single entity for forwarding the packets. And different types of groups are provided in the specification to represent different forwarding abstraction, like multicasting, like broadcasting, like unicasting, and things like that. Now, each group table will consist of a number of rows. As we just saw in the case of the flow tables, we have a number of rows, and the rows, as I just mentioned, they are called entries, but in this case we will refer to them as group entries, not simply entries. And remember the columns, which we refer to as components. So inside the group table we have 4 components. The first one is identifier. That is the group identifier, which will uniquely identify the group. A group is defined as an entry in the group table. So like if we have a class and we have 4 different groups, and we identify each group by a number, like group number 1, group number 2, group number 3, and group number 4. So we need a group identifier. Group type, to determine group semantics. Like every group number 1 is working on database, group number 2 is working on networking, group number 3 is working on web, and things like that. What is the type of the group? And the counters, and you know the concept of counter, means they need to be updated when packets are processed by a group. Total number of packets received, total number of packets transmitted, drop, etc. And the last component is very interesting and important. That is known as the action buckets or buckets. It is actually an ordered list of action buckets where each action bucket contains a set of actions to execute and associated parameters related with those actions. So each group include a set of one or more action buckets, and each bucket will contain list of actions. So now we are talking about the buckets and the actions. The action list in a bucket is executed when packet reaches a bucket. This is important. When you have a packet which arrived, which reaches to a bucket, then the list of actions will be executed, and the action list is executed in a sequence. Okay, so here is an example, and you can see that a group is actually designated as one of the types that are actually shown here. Like we have all, we have select, we have fast failure group, and we have indirect group. And you can see from the figure, like for example the first one where the type is all, it executes all the buckets in the group. What does it mean? Each arriving packet is effectively cloned. Means each bucket will designate a different output port. How? For example, the incoming packet, you have an incoming packet to the bucket, then it will be transmitted on multiple output ports. In the terminologies of networking, this group is used for multicasting and broadcasting. Like you have a packet, you make copies of that packet and you send them to all the buckets. Or in other words, you forward the packet on all the output ports. Okay, that is why it is called all. On the other side, the select, random select, executes one bucket in the group. You see, you have three buckets, but you are executing only a single in the group. And that decision is based on a switch computed selection algorithm. Like which bucket you need to select. So we need an algorithm for that. And that could be based on several parameters. Like we need to share equal load. So who is actually with less load, you assign it to that bucket. Okay, so load sharing based on bucket weights, for example, and this is the responsibility of the SDN controller to decide which packet will be put in which bucket. The third one is fast failover, and this is simple. Execute the first live bucket. The buckets are evaluated in order, and the first live bucket is selected. Like for example, the port liveness is managed by the SDN in this case. Okay, but that is outside the scope of this lecture. How? For example, this port is not responding, for example. So what is next in the active list? Select it. And then we have the indirect. It allows multiple packet flows to point to a common group identifier. This type provides for more efficient management by the controller in certain situations. For example, suppose that there are 100 flow entries that have the same source and same destination IP address, and the field is match. Okay, but the source and destination addresses are same, but maybe they are different in some other field. Okay, so in this case, all the packets based on the common fields, they will be forwarded to a common port. Common bucket mean common port. For example, port number X. And the action performed in this case is that, okay, send all the packets which belongs to the same destination IP address, for example, on the port number X, okay, because they have same destination. So this is like unicast, you can consider it, okay, all the packets for the same destination. Well, this was about what's happening inside the group tables. What are the different actions that we can actually perform and how the packets are sent from the flow tables toward the group tables. Okay guys, OpenFlow, as I mentioned earlier, needs several lectures, and we will dedicate some of our lecture to study OpenFlow in detail. So at this level, if some of the concepts are not clear related to OpenFlow, I'm sure it will become clear to you in the coming weeks. Thank you so much for attending the lecture. We will have a discussion in the synchronous class. See you then. Goodbye.